we were talking about linear equalizers, and specifically we were talking about using FIR filters as equalizers, and we can have the FIR filters at the receiving end or the transmitting end before transmitting the data. Okay. Now you have a linear equalizer of some finite length. The question is how you choose the coefficients, and we came up with a couple of strategies for doing that. We did it somewhat intuitively using time domain arguments. Later, when we have time, we'll also formalize the whole thing. These things work for not just binary data; it works for any kind of data and so on. So they are very general, but we are trying to get a flavor of the results by walking through the arguments instead of just doing a mathematical analysis and saying that this kind of filter will work. Again, the system we have is binary data. So this transmit filter is the one which determines the shape of the transmit pulse, and this goes through a channel. The output of the channel is sampled, and this is fed to a discrete time filter. This is the kind of system that we have assumed so far, okay, or an equalizer, and this is fed to the decision block, okay. And we started off by looking at very simple models for ISI and the filter. So let's say the response to a single pulse of this part looks like this. Now to this can be equalized by, this has an ISI with one tap. This can be equalized by another FIR filter, and it can have more taps if necessary. And we saw that as we increase the number of taps, the residual ISI can be reduced. Okay. And the first strategy was to make the response of the channel plus equalizer equal to 1000 as much as possible. The last one you can't, that you know. Okay. If you had to make it 1 and all zeros, what would you need? What kind of equalizer would you need? IR. Okay. Essentially, if this is the transfer function of this is the discrete time transfer function of the channel plus sampling. Okay. The transmitter plus channel plus sampling. So to equalize it exactly, you need this to be the inverse of that channel plus transmitter response. Okay. How is this related to the equalizer that we designed? Does it have any relation? Okay. And what do you do? If I expand this in a power series, I get infinite number of terms. So let's say, if I use this in an expansion, this will be some series with infinite number of terms. Is F related to G in some way? We said that G is chosen like this. You choose G so that the response of channel plus equalizer is something like this. 1 and 0s as many as possible. Huh? F is equal to G. Yeah, F. In fact, this is nothing but just truncated part of this one. That's all. Okay. So you truncate it, and that will, if you didn't truncate it, you will get everything to be 0. If you truncate it, you get a certain number to be 0, and the last one will become non-zero. That's all. Okay. So this is nothing but G of Z. You get the FIR by truncating the inverse of the channel. So essentially, you try to invert the channel, but then you cannot really make IR filters. That's our assumption so far. So you make FIR filters, and you truncate it at some point, and that gives you this kind of response, which will have 1 and all zeros except the last one. So this type of an equalizer is known as a zero forcing equalizer. Zero forcing equalizer is nothing but the inverse of the channel, but in cases where we cannot make the exact inverse because the impulse response is too long, you truncate it and go with it. Okay. Any questions on this? What can be a problem with the zero forcing equalizer? Okay, number of taps required. That may be too large, yeah, but what else can you see? See, basically you are trying to invert the channel. Yeah, so the problem is that let's say your channel response, that is the magnitude of HCH looks something like this, okay, and this is the omega axis where this is about, this will repeat, right. So let me just show it up to half or something. So it looks something like this, and the whole thing will repeat because it's a discrete time response. So what happens is, now where in the at frequencies where the attenuation of the channel is large, the amplification provided by the equalizer is also very large. Okay. So let's say you have our usual channel plus equalizer model. Okay. Now let's say some noise is added to it, and this passes through the equalizer. Okay. So now this noise is only the equalizer's transfer function. You are trying to make the cascade of this and this 1. That means that wherever this has a large attenuation, this will have a large amplification. Okay. And if your channel happens to have a null or a notch, so let's say it looks something like this, then you will have to have infinite gain at this particular frequency. Okay. So this is the response of the channel, this is the response of the equalizer. So if you try to do zero forcing, this is what you will have to do. Isn't it? Is this clear? Essentially you get the gain of the equalizer is inverse of the gain of the channel. And where the gain of the channel is very low or the attenuation is very high, the gain of the equalizer has to be very large. So that means that the noise at those frequencies will be amplified by huge amounts. Okay. So in presence of noise, this may not give you the best result. So even if, let's say, the number of taps and all those things are okay in absence of noise, the taps are reduced to 0 and the last one is small enough. But then when you add noise, the amplified noise can give you worse signal to noise ratio. Okay. Okay. So an idea that is proposed is, if we have the equalizer at the transmitter end, we will not have this problem. Is this correct? What can be a problem with this? Actually, that's a very good idea. So let's say, firstly, everyone is convinced that I can put the transmitter in the, I can put the filter, equalizing filter in the transmitter or the receiver. So this is, let me redraw it below. I have the discrete time and the transmitter, and the channel, sampler, and the decision. So the two places I can have the filter are, if I have to have a discrete time filter, I can have it here or I can have it here. Okay. I said that if I add noise samples to this point, then that will experience a large gain of the receive equalizing filter. But he is saying that if I put the filter here, then this filter is no more, the noise will go through a unity gain. What is the potential problem with this? Adaptation may not be possible. Okay, let's say we are not worried about adaptation. Pardon? Yeah. Okay. No, we are, right, because see, what matters for us, the response for the signal is the product of the channel response and the equalizer response. I can put the equalizer before or after the channel. So as long as I assume linearity, there is no problem with that, okay, as far as the response to the signal is concerned. Yeah. Actually, the question is, what is the signal strength here going to be? Okay. See, after the channel will attenuate your signal and then you amplify it back. Here you are passing through the filter an unattenuated signal. Okay. So this is the input signal spectral density, and then you pass it through a filter like this. So the signal strength here is a lot more. So you have to transmit a lot more power. Okay. So eventually it will come to the same thing. So even in the other case, if you this is random noise and the noise is not related to the signal, let's say the amplitude of noise is not related to the signal. Okay. In the one case, when I have, let me draw it separately. So in the first case, I have the channel, sampling, and then the filter, okay, and then the decision. And I assume that some noise samples are added here. Okay. And in the other case, I can have the filter which goes through the transmit pulse shaping, which then goes through the channel and noise is added. Okay. And you have the decision. So if you use the same equalizing filter here and here, the signal strength here will be much larger. Okay. Is this clear? Now you may not be able to arrange to do that. For instance, in a practical transmitter, there is a limitation on voltage. Okay. There is a limitation on the maximum voltage that you can put out. So that means that you cannot really amplify the signal too much. Okay. What you will have to do if you do this is, let's say the shape of the equalizing filter is like this. To keep the signal strength here at a limited level, you have to reduce the gain. You can keep the same shape, which will keep the equalization, and then you have to reduce the gain. Okay. Now your signal strength has reduced. So it's not immediately obvious that this is better than the other one. Okay. In some cases it may be better. In cases where you, like for instance, you do pre-emphasis and those things in FM, it may be better. So the problem with this is that the signal that you have to transmit is now much larger, which may not be, firstly there is more signal power, and because of practical limitations of circuit, you may not be able to accommodate a larger transmitted signal. I mean, you may not be able to transmit a larger signal. Okay. Because eventually what you are concerned is with an efficient overall solution. So instead of burning a lot of power in the transmitter to transmit a larger signal, you may be able to do better by using the same power to make a better equalizer in the receiver. Okay. So that is one issue with this. Now there are two kinds of interfering signals. One is this noise, which is, in this case I assume this is random noise, and this has nothing to do with the signal. Okay. And do we have interference that is related to the signals? Related to like signal strength and so on? Crosstalk. So in case of crosstalk, we assume two identical channels. Okay. Let me draw that. I will skip the discrete to continuous time conversion in this. I will just show it as a single discrete time channel. Okay. So I can have discrete time data. I pass it through an equalizer, and then I pass it through the channel. This channel is implied to have in it the transmitter pulse, the actual channel, and the sampling. Okay. Everything is included in this. This is a discrete time channel. And then I have the decision. Okay. And this is, let's say, one of the channels. And I have the equalizer and another channel. This data is uncorrelated to this. So this is data 1, this is data 2, and this is number 2. And then there is coupling. Okay. Now I can have the same scenario with equalizer at the receiver. That is, I have two channels with coupling between them. Which is better? In fact, I had asked this question in class once. If there is a way to arrange the filters on the transmitter side and the receiver side to optimize the results for crosstalk. So which of the two is better? So now let's not assume any random noise that is added, right? The only thing is, let's say we are looking at channel 1. This is our channel, and channel 2 is interfering with it, and that's the same thing in this case. Okay. Here I have equalizer in the receiver. Here I have equalizer in the transmitter. Which one is better? Coupling will be much more in the first case. So, okay, first let's stick between these two, right? Yeah, you are saying that you want to optimize it further. So, but between these two, which is better? Is there something that you can say? He is saying that the first one is worse, right? Yeah. The second case, the crosstalk will also be? Okay. Okay. No, one thing you have to assume is that the two channels are identical, meaning they are not transmitting identical data, but you want similar performance from the channels. Okay. So that's true, yeah. In the first case, you are amplifying it more. So, but which is better?
Which is crosstalk is also more than the ratio is
Both are equally bad.
the ratio is
Ratio of what and what?
two cases.
In the two cases. There is no noise. Ratio between what and what?
Ratio to signal, from signal to crosstalk.
Is it the same? It is. Huh? Both are the same. Oh, okay, that's the other thing. I mean, is this equalizer the same as this equalizer? No, I don't know. I want to transmit properly. That is my goal. Okay. No, I mean that clearly is not ISI, right? Because ISI relates to the same data stream. Okay. So the term ISI refers to if you have a sequence of symbols A0, A1, A2 and so on. A0 affects A2 etc. Okay. Not from a different data stream. So what is it? Okay. Okay. Yeah. Actually, I was hoping to have this question in the exam, but you won't. So the coupling can be modeled as some filter, right? Meaning I have two channels and there is some coupling. Okay. And I am also assuming a symmetrical scenario. So between this point and this point, let's say 1, 2, 3, 4. There is some transfer function between 1 and 2. As long as I assume linearity, I can model it like this. Okay. And between 3 and 2, it will be some crosstalk transfer function which is added to this. And here again I have the channel and I have the crosstalk. So this is just a consequence of linearity. So whatever it is, I can reduce it to some transfer functions like this. And also I am assuming a symmetric scenario. So this and this and this and this are all the same. Okay. Meaning these two crosstalks are the same and the two channel responses are the same. Okay. So now what is it going to be? I am interested in, I have data here and I put a filter here. Okay. What do I receive at this point? What is the signal? So let me call this x1 and x2. Okay. The two data are x1 and x2 and it goes through the system. So what do I receive here? What is y1? x1 into H equalizer times the channel response plus x2 times H equalizer times the crosstalk. Okay. Let's say instead I made a new system where I have x1, x2 transmitted here without equalization and I put the equalization afterwards, and this equalization may not be the same as the one before. This is some other, and then now my new y1 and y2 are here. Okay. What is y1 now? This is with the transmit equalizer. What is it with the receive equalizer? Plus x2 times the crosstalk times the new equalizer. Okay. So firstly, how is HEQ prime related to HEQ? Would you choose them differently? No, let's not worry about saturation and all that. Let's assume pure linearity. We want them to be the same. See, equalization just refers to what this whole thing looks like, right? Essentially, this is the transfer function that is multiplying x1 and this is the transfer function that is multiplying x1 here. And maybe like in equalization, let's say we use the zero forcing strategy, then we want this to be flat. We want HEQ to be inverse of H channel, and here also we want HEQ prime to be inverse of H channel. Okay. So the equalizer response that you would choose in the two cases is the same, because we optimize it for the signal. We are now assuming that we are not looking at the crosstalk and doing something else with it. Okay. So the two equalizers are the same. So what is the signal that you get? It's the same. So it doesn't matter if you put it in the receiver or the transmitter. The response will be exactly the same. Because basically the bottom line is the crosstalk goes through the similar transfer function. So if you increase the signal, then the crosstalk also increases. That's why you can also not play around by increasing the amplitude of x1 or x2. Okay. Of course, we are operating under the assumption that both channels have to work properly, like x1 to y1 and x2 to y2. You can always make one of them better by attenuating the other one, then the other channel will behave a lot worse. Okay, both of them should work well. So you receive exactly the same signals. So the crosstalk goes through the same transfer function. Once you decide the shape of the equalizer, okay, whatever strategy you choose to you do zero forcing or you choose to do something else, you will do the same thing in the two cases. Okay, there is no difference between the two cases. So HEQ is the same as, the two equalizer responses in the two cases are the same, and the crosstalk is also the same. So the interfering signal is exactly the same in the two cases. Once you choose that a certain equalizer is good enough for you, then the responses that you get is the same in the two cases. So it doesn't make any difference whether you put it in the transmitter or the receiver as far as crosstalk is concerned. Is this convincing? And this is under the assumption that everything is linear. Okay, there may be some practical considerations, like you mentioned that maybe if you put the filter in the transmitter, you have to transmit a very large signal. So such things may be there. Otherwise, there is no difference. Okay. So the bottom line is, if you have uncorrelated random noise, then when you have an equalizer, it tends to amplify in some region where the channel attenuation is very small. Especially if you choose a zero forcing equalizer, that strategy necessarily amplifies the signals a lot, where the channel attenuation is a lot. Okay. So the signal to noise ratio in some frequency band will necessarily get much worse. Rather, the noise in some frequencies will get much worse.
For that matter, the equalizer will have the same.
Any equalizer?
Will have the same.
Well, you may choose not to amplify it so much. Okay. Yeah, the question is, will that problem not be there in other equalizers? So let's say the response of the channel is something like this. If you do zero forcing, you will exactly invert the channel. You will exactly invert it. So when the channel attenuation is very large, the gain is also very large. What does zero forcing do? It minimizes the ISI, okay, but can amplify the noise a lot. And what you care is not just for ISI, what you care about is signal to noise ratio. Okay, so what you care about is signal to noise ratio. So you can choose something that doesn't amplify it as much, which will have more residual ISI, but then doesn't amplify the noise so much. So that may be better. Is this clear? Because it's the combined effect of ISI and noise that hurts you. It's not enough to optimize it for ISI. If you invert the channel exactly, you will optimize it for ISI, meaning you will have no ISI at all. But then you have gone and amplified the noise so much that maybe that is not the best choice. Maybe you choose a compromise filter where it doesn't boost the signal as much. Maybe the response of the equalizer should be something like this, where because of limited boost there is some ISI, but the amount of amplification of noise is also smaller, so the overall result may be better. So again, if you have a channel and let's say white noise is added to it and you have the equalizer. Now it turns out that I will now state this without proof. Later again we will go into the more mathematical aspects of it. So again, the question is how to choose the coefficients of the equalizer. One way was to do the zero forcing, and then now we see that can amplify the noise a lot, so you can have problems. So another way is you take the response of the channel plus equalizer, that is, you take this product, and if you look at this in the time domain, you will get channel response convolved with the equalizer response. Okay. Instead of trying to make this 1 and all zeros, you can try to minimize the mean square error in the intersymbol interference paths, okay, except the first one. So let's say you make the first one 1 and you minimize the mean square of the rest of the stuff. So you choose the types of HEQ so that you minimize the mean square error of the rest of the stuff. It turns out that is the best case. That is much better for noise. Okay. So the channel and equalizer is the total response. Okay. You minimize. So here I assume that 0 is the cursor. Okay. So you take out the cursor, you minimize the mean square error, sum of the squared errors of the rest of the stuff. Okay. Now none of them may be 0. In fact, none of them will be 0 generally. But the overall effect will be better. So you can do that. So that's what you will get, right? So if you look at the spread of values around h of 0, you will have a bunch of values. Okay, so if you exclude h of 0 and minimize the mean square, I think that is what we will get. Yeah, so H total is this, something, okay, something like this, and H of 0 is this. So if you take these two, if you subtract this from this goes away, isn't it? Is it, or you think about it? That should give you the right result, I think. Yeah. So that is assumed, meaning that's true. Now see, the one thing is you can change the gain of the equalizer. You can increase all taps by the same amount. It won't change the, let's say, the quality of the signal in any way, right? If you change all of it, it will simply change the amplitude of the signal. So we have to have some constraint on one of them. Otherwise, it becomes totally arbitrary. So let's say the main tab, you adjust the gain so that the main tab is 1, and then the rest of the stuff you minimize. Okay. So we can, I mean, it is the same thing. You can think of adjusting all the tabs of the filter, but it is all usually, especially for circuit design, it's more beneficial to think of as you have some gain of the filter, and that gain you have to increase if the ISI is large, because the main cursor tab keeps on reducing. And then once you fix that the main tab or the gain of the filter, then you can adjust the rest of the stuff to do equalization. So it's actually, you really have only, if you have 3 tabs like this, then you have only 2 degrees of freedom, the ratio of this to this and the ratio of this to this. That's what you want to adjust for equalization. Now in presence of noise, this turns out to be the optimum. We'll see later exactly how it comes out. No, it's not. Because why is it the same as crosstalk? No. White noise is not crosstalk. The main difference is, see, when we think of simultaneous channels, then like what happens for one channel happens for the other channel. Okay. So in a way, if you amplify the signal in some way, the crosstalk channel also gets amplified in the same way. That is not true for white noise. But this scheme may be better for crosstalk also for this reason, right? When you do, let's say the channel has this attenuation, to boost it up, to do zero forcing, you will do something like this. To do this minimal mean square error, you may do something of this sort. Okay, less boost. Now you also know that the crosstalk itself increases like this. Okay, with higher frequencies. So you have less boost where the crosstalk is maximal. So it may do better for crosstalk as well. It will do usually better for crosstalk. And this way of choosing the coefficients is known as MMSE or LMS. So this is just like different acronyms for the same thing. So this says minimum mean squared error, and this just says least mean square. Okay. The mean and they are the same thing. Okay. So the two equalization strategies that we know are, one is zero forcing and the other one is minimum mean squared error. Minimum mean squared error works better in presence of noise. We have not proved how it is, but for now we will say that this is a strategy of choosing the coefficients. We will see how to implement some of these things and then come back to more theoretical. Why? No, firstly we are talking only about discrete time. So far we have only talked about discrete time stuff. So there is no meaning in talking beyond fs by 2. Right? Everything repeats every fs. So when I draw plots like this, it's assumed that the limit of this is fs by 2. Does it answer your question? Are you saying that there will be no boost beyond fs or fs by 2 or what? So we are only concerned with frequencies from 0 to fs by 2. Okay. When we talk about discrete time stuff, it's not because of any low frequency limitation or something. The repetition of the spectrum is inherent to sampling. Any questions on? So we have a low pass channel typically. So it has attenuation at high frequencies. I will draw stuff only up to fs by 2. Okay. This is the channel, and the channel has high frequency attenuation. Then the equalizer needs to provide high frequency boost. This much you can intuitively guess that it is attenuating high frequency, so the pulse is getting rounded off, so it is interfering with many other pulses. Okay. So if you provide high frequency boost, things will get better for a channel. But then there is not just a channel, there is crosstalk and noise and other things. Okay. So we have two ways of choosing the equalizer types. First is just try and invert the channel. This is what we do with the zero forcing equalizer. Okay. Ideally, this will be IIR, and we truncate it, and we use an FIR filter to do this. Okay. Now, this has large gain where the channel has a large attenuation. Now, if you didn't have any noise and any other signal, this would be the best because you get 0 ISI, and that's what you use. But then you have noise also, and that gets amplified precisely where the signals are small. So maybe you are better off leaving some of the ISI, leaving some of residual ISI be there, letting some of the residual ISI be there, but amplifying the noise a little bit less. Okay. So this is this gives you a large gain for high frequency noise and crosstalk. Okay. So alternatively, you don't do zero forcing, but minimize the mean square error in the channel plus equalizer response. Okay. So this compromises the boost at high frequencies where the channel attenuation is very large, but then what it gives you is it doesn't boost the noise as much, so it is better for noise. This typically gives you a lesser boost, so it's better with noise, and also typically crosstalk, because crosstalk also tends to be maximum where the signal is small. So as you go to higher frequencies, the crosstalk tends to increase a lot. So these are the two ways of choosing coefficients. You can try it out in the assignment and see what you get. Okay. But there is a single channel, so you may not be able to. I don't know what you will see. You just try it out and see what you get. Any questions on any of this? So all of this can be formally proved. It's not that it approximately works or something. So it works quite well, and we'll see all of that later. What's that? Yeah. Perhaps, yeah. There are different kinds of coding. There are simple codes and more complex codes. Firstly, we may not be allowed to use a code, meaning maybe the standard will specify that you have to transmit data in this format. That may be the case. And maybe, well, coding also has some other disadvantages, right? You need more hardware and so on. So including all that, maybe it becomes worse. But yeah, if you have complicated coding, you can certainly do better. With the same signal to noise ratio, you can get better bit rate, right? That is the idea of coding. Okay. But then you also have to introduce redundancy, so you have to wonder what that will do to the channel. Okay. Meaning, you have to transmit more data and receive less data, right? That is the idea behind coding in general. Any questions? Anything else? So you mean zero forcing and this one? Why? Oh, any condition under which this will be the same. No, these two are totally different, right? In one case you try to, I don't know, maybe if you have only one tap, no, even then I don't see any, you have something like this, and in the other case you try to maybe do something like this. So I don't think it will be the same. I mean, I don't know, I don't have a mathematical proof of it, I'll think about it, but I doubt that it will ever be the same. Yeah, which is equalizer has only one tap? No, that also not necessarily, right? You mean there is no equalizer? Yeah, okay. So I got confused whether by one tap you meant the cursor and one extra or just one. Yeah, so in that case, yes.